Okay. I guess I'll make this informal given the group is smaller, so that is easier. Feel free to ask questions anytime and so on. Yes.
Who are you?
Okay. So my name is complicated. I go by KK. I'm from Stanford. I work for Professor Nick McKeon, Guru Baruka, and more recently, Sachit Kapil. For people who read sitcom papers, you will probably know. So I want to talk about my work for the last 2 years where we look at mobile networks in general, networks architecture, and more recently, network measurements. So motivation, this will be a very short motivation. I think yesterday's speaker already motivated this enough. So mobile network is becoming all IP, right? LTE and WiMAX are being deployed. WiMAX more than LTE because WiMAX is somewhat 2 years older than LTE is. LTE probably has like deployment in Britain and Japan, that's all right. While WiMAX is deployed Malaysia, Russia, whole bunch of Southeast Asia countries, East Asia countries, and so on and so forth.
There's a strong deployment in Korea, apparently.
Pardon?
There's a strong deployment in Korea, apparently.
There is, but it's not WiMAX, it's Wibro. Wibro is a sub-profile of WiMAX, which is not based on 802.16e, but 802.16a. So it's static WiMAX, it's not mobile WiMAX. And if you push the WiMAX base station around, and people who know WiMAX is around, just joke with them. Tell them it's mobile WiMAX. Okay? Mouse move. Okay. Didn't like me. So, mobile usage is becoming more data. So the 3G and even 2G networks are not designed to carry that much data. Clearly, AT&T is having that problem, and they're not too happy about it. Now that they have cut the plan back to, I'm going to charge you for every bit that I'm carrying through my network, right? So their backhaul is actually very ill provision for such things. But this is definitely changing in the 4G world. 4G is very data-oriented, and voice is a special class of data, rather than data is encapsulated in voice packets. So IP is really poor in mobility and security for all we know up to now as academians, right? But this is precisely what we need. The mobile networks needs to securely extract money out of people that is using their network. And now you can't determine who to get their money from. That's a very bad idea. And these people are driving in a car. So what do we really want? What we really want is low latency, high throughput, and perfect coverage. Perfect in some extent. If you live in a Faraday's cage, then a bit harder to get that. And maybe free, but free, I'll talk about the free part later. So wait, low latency, high bandwidth, and wide area coverage, isn't that 4G? So we'll study an incipient commercial WiMAX deployment to investigate. Is that true? Is 4G going to deliver that low latency, high throughput, and wide area coverage, right? That is at least the claim that Sprint and the other guys are going by. So in this network, there's no limits on the rate, meaning the traffic is actually not throttled. We are actually using an innovation network, so there is not much traffic on it. So think of this as an informal best case, because the network is basically unloaded. There's like 5 users on the network. That includes like up 20% of the only one actively using the network. So this is a 4G WiMAX network. It's deployed by Clearwire. If you look at the graph, the picture over there for Google Maps, this is actually the signal strength that we have observed on the 2 sites, one on Stanford University itself, the other one on the city of Mountain View. The only reason why Mountain View is covered is because Google is there. And they have a few base stations there. This network is actually deployed professionally because they're going to turn this commercial at the end of the year. So in terms of equipment grade and everything, this is fully commercial. We are not having a bunch of academians putting up WiMAX base station, James is doing. But this is actually professionally deployed by people that knows how to survey networks and know how to deploy networks. So how do we measure this? This is how I measure it, a laptop. So we only use cost equipment. So nearly everyone can do this. So one of the myths about measurements of mobile networks is you need those bands with satellite dish on the top and antennas sticking out on the top of the car. Not true. You can actually just get GPS. In fact, this is the GPS I use. a laptop, a modem, and some custom Python script, and you can really rip out a lot of information out of those networks. So we did two types of tests. One, we did a driving test in which we logged the location, the time, and the signal strength. So for a driving test, you can't really afford to do too much. And a static test. So a static test is where we stop at a location. So to make sure that the tests are comparable, we did not move equipment out of the car. They're all powered over the car battery or with the engine running, so there's no power issue as far as we're concerned. The location, time, SNR, and we even did IPER for throughput, UDP, both uplink, downlink. We did a latency test for RTT and trace route.
What is CINI?
CNR is what they call carrier interference and noise ratio. So okay, I'll go a bit into CNI and RSSI. The difference between RSSI and CNR is actually fairly crucial. This is a difference that's coming up in recent years. Modern chipset, by modern I mean like the last 5 to 10 years, chipset starts to have something called CNR, where the carrier of the signal at the end of the demodulator is compared to the interference and noise that the receiver sees. That is as opposed to RSSI, which is just the power that the RF front end receives. So one you can get just pure analog, RF front end. The other one you actually need a demodulator there to demodulate the signal and get it. So there must be a carrier signal. The signal must be actually modulated correctly. If not, you get nothing. You'll be zero. It will be negative something, dBm, right? So that is what CINI is. Think of it like a signal to interference and noise ratio, literally, of what the receiver sees. But then again, receivers will differ in what they consider interference, because some of them do interference cancellation, break receivers, and so on and so forth. So you'll be very slightly different. Okay. So let's look at some numbers to start with to get an idea of what the drive test will like. So for a drive test, we take anything from 1.3 seconds to 12.7 seconds. Latency is simply because the GPS sometimes lose something and you wait for the GPS to acquire the location.
So
and
what is 1.3 to 1.7 seconds?
That's the duration of each test, how long it takes to complete one loop of taking a location, the time, and the signal strength.
While driving.
While driving. So this is pardon?
Why it fluctuates between these
Correct.
numbers?
Correct. So this is max and min. This is not even standard.
Why? Does it depend on the speed or?
It depends on both the speed and also where you are. So if the coverage is bad, you tend to get the signal strength really slow. Right? So because we get CINR, the receiver doesn't really like the fact that you keep polling for CINR and like, I'm having bad coverage. What is my signal strength, right? Trying to acquire that carrier.
It depends on distance between base and mobile.
Correct. So it depends on not just distance, there's a variety of things. I'll get into the distance thing in a while. We'll look at path loss. So for static test, it's definitely longer. Each one took at least a minute. It was designed to be a minute, and we are looking at about 66.9 seconds on the average, and we're looking at standard deviation about 13. So it at least took a minute. So this is actually slightly on the heavy tail side where I couldn't acquire and this thing just drags on. So this means I actually stopped the car, have the engine running, and took the test there.
Why is it so long compared to?
60 seconds is because when you do your IPER, you did 10 seconds uplink, 10 seconds downlink, TCP for 20 seconds, UDP for 20 seconds, your 40 seconds gone. You do a ping test, that's another 5 seconds gone.
All those things you're not doing in the driving test.
Of course not. Because think about it, if you just do a 60-second, 1-minute test on the driving, where do you attribute that measurement in terms of location, right? You just covered, like, if you're on 101, 65 miles per hour, sure. You just went over to like 2 base station now, it's too late. So static test is something that is more for performance, because what the end user cares about is things like delay, throughput, and so on, right? Signal strength, why do I care? If I get my good connection, I get my good connection. But it's impossible for surveying teams to do this everywhere. So this is actually where I did the survey on Stanford itself. That brings me to this. So in Stanford, we actually have 1,000 over readings, nearly 2,000 readings for driving tests, much easier to get. And we only have 75 static test readings. On top of it, on Mountain View, we only did driving tests. It's nearly 3,000 readings on driving tests. And I can tell you, Stanford plus Mountain View driving test took as long as just 75 static tests. So static test reading are extremely difficult. They are a pain. So you really have to find a spot that you can stop your car without getting the traffic police behind you and so on and so forth. Okay. So let's take a look at what we see, right? So we take a look at the signal strength. This is the CDF of the signal strength. Sorry, I did not really label the y-axis properly. So the x-axis is actually the CINR, and on the top is the other x-axis, that is the RSSI. So on average, we are looking at a CINR about 17.6 dBm. So if you look at about negative 72.5 dBm, sorry, 17.6 dB. So CINR is not dBm because the reference is not 1 milliwatt, but the reference is the noise and interference ratio. So definitely, if you look at this, these spots are present, right? These spots we define arbitrarily at if CINR is below 3 dB, which means your received power in terms of signal is half or twice of that of noise and interference. Anything slightly below that, actually, you can't really communicate.
Did you also plot the SNR?
SI?
So you plotted power and SINR. Did you plot the
SINR is similar to CINR.
Yeah, I said it. That's why I said like CINR is similar to SNR, and you plotted received power, which is your RSSI. Did you plotted also SNR? I mean, which is like in your case CNR, not CINR.
Oh no, we won't know that. The thing is that the receiver will treat interference as noise. So the receiver is not designed to actually differentiate between interference and noise. So surveying teams in general use both RSSI and CINR for that reason, because there's no obvious way of measuring interference. So what you do is you take a look at the received power that adds up additionally, while CINR things like wave are actually constructive fields, so you actually see the differences. So you get very good RSSI, but hey, wait, the CINR sucks. It's probably due to interference. That is how they sort of empirically deduce. So they don't really care about exactly like, oh, this 1 square meter has bad reception. They will ignore it because it's just a fact of life, right? It's not economically viable to fix every single problem that you find. And if you note the way driving tests are done, or this type of surveying is done, is exactly what professional does is on a car. So indoor, zero reading. Indoor surveying is a complete dark magic art. Nobody knows how to do it. Okay? And from even just innovation network deployment from Clearwire, right, we're looking at actually a fairly good coverage. We're looking at 82.7% of the area we surveyed actually are very well covered, meaning 10 dB and above. We get very good signal, you can serve decently. You can definitely do most things that people would want to do on the network on 28.7% of the area. And that is to note that I did drive slightly out of the coverage area that they claim. Right, but because it is not a fully covering network, so we don't really know how much holes they will leave and so on and so forth.
How do you define dead spots?
This spot is defined as 2 dB, 3 dB and below.
I'm sorry?
3 dB CINR and below, which means power of the received power is 2 times of that of interference and signal and below.
So what is between 3 and 10?
Pardon?
What is between 3 dB and 10 dB?
10 dB is just, I will show you later why we use 10 dB. 10 dB is just where we observe that the internet is actually more usable.
I see.
So anything below 10 dB is actually not that great.
So what is the range between 10 dB and 3 dB? Is it It's not usable and it's not a dead spot. It's not usable.
That's when you get intermittent connection and you get frustrated like, oh yeah, I can surf my web. I can surf my web. Yes, I can surf my web. No, I can surf my web. That thing. It's approximately what Wi-Fi is like on James' seat. For the last 2 days experience. So it's barely usable. You can probably use it to check email because that syncs once in a while when you aggressively poll and you get your email down, suddenly you get your email. And when you send your email, most phones don't send them immediately.
Are you saying it's time varying?
It's not only time varying, it's also location varying depending on how much you move. This is the flood. This is all the gray area, right? Where you move a bit and you get this better signal, and you move a little and you get this lousy signal, right? It's that sort of network that you don't want to be in, but you sort of still have network, that thing. Okay, I'll give you more quantitative data on what exactly that means in terms of throughput and everything. So let's look at group put. I'm using group put simply because measurements people in Silicon community tends to use group put for hyper, which means the data that goes through minus the overhead of Ethernet and so on. This is usually used for user level metric because throughput is just raw bits as far as they are concerned. Okay, so group put is what hyper gives you. For TCP, we're looking at about 0.81 megabits uplink and 2.49 megabits down. This is TCP. Okay, what this means is just channel asymmetry. This will always exist in mobile networks because the base station has a lot more power and it can afford directional antenna and everything. So it can deliver a lot more to you than up. Okay. And take a look at UDP, we can actually get about 2 megabits up and about 7.4 megabits down. So the CDF is actually shown on the right. The picture I think is not coming up perfectly, but I will put up the technical report somewhere so that you can take a look at the numbers better. In fact, we're going to make this data set publicly available because we measure it off ourselves, so there's no restriction on what we can do with it. So latency. Latency is this mysterious thing in mobile networks where the 4G claims to be low latency. We are looking at a jitter of about nearly 20 milliseconds up and 5 milliseconds down. If you use Wi-Fi, you will consider this latency huge, right? Just the jitter itself. But this is without QoS. I have to quantify myself. WiMAX has 5 class of QoS that is compulsory. It is without QoS. And it is not, Clearwire at least has not publicly announced if they will support QoS in the short term. In the midterm, they are trying. At least Spring is claiming they will. And we're looking at RTT of 94 milliseconds. This RTT is between our server in Stanford that has like latency of 5 milliseconds to everything else that is connected to a university network. So most of it is in the network. Even if you ping their gateway itself, it's 85 milliseconds above. What is worse is that they have this occasional spikes in RTT. So if you look at the time series on the bottom graph, this is the RTT measurement. It actually goes up once in a while. The reason for the RTT spike is unknown. This is very common. So we know about throughput, we know about performance, but how do you relate this to a wide area, right? Because this is over 75 readings only because it's impossible to get better readings. So we take a look to see if there's a correlation between signal strength and good pull and delay. Because that will give us an idea of, is this good? Is this, can we induce something out of this, right? Can we deduce something out of something that we can measure very rapidly? Can we use that to induce something out of the performance that we really care about?
So can you just quickly define latency?
Latency is, so there is 2 latency. If you look at latency, jitter is based on UDP, uplink and downlink iPerf. So iPerf will send things out at regular rate, it will timestamp it, and it can calculate the jitter. One-way delay cannot be measured unless you have synchronization, and we don't. The fact of network today. And RTT is based on ping. So you will just send a packet there and back. So you can measure RTT, you can measure jitter. You can't really measure one-way delay. One-way delay is still a mystery.
Jitter is?
Jitter is just how much each packet differs, varies from
like
the
a
regular
variance.
interval. Yes, it's more like variance. Standard deviation, yes. Variance will have a different metric. Like, okay? So, we take a look at the signal strength and ask ourselves, can we induce something out of this? The signal strength can be in terms of CINR or RSSI, right? And in fact, these two metrics is actually very well correlated. They actually have correlation coefficient of about 0.87, which is very high if you study probability. And we take a look at good put and bad, right? That graph is slightly dense. The paper actually have a more sparse graph where this graph is split into two. We are looking at CINI RSSI of correlation of like 0.9 for downlink for TCP, uplink UDP, and it's about 0.9, 0.7, 0.8. They're all in the high range, except for one thing that has puzzled us. Uplink TCP, uncorrelated. We have no idea why. It could be due to the latency, so your RTT actually did not come back fast enough.
You don't have much. You don't have interference from the other mobiles. Therefore, your CINR is very close to your CNR. Actually, this the slope of your curve here, it is should be somehow related to your noise power. It's at the receiver, and the fluctuation around that curve should be related to the interference you are seeing. In the uplink, you don't have that interference from the mobiles because base stations are much more capable.
Correct. Base station is definitely much more capable of receiving signal because they are much bigger rate receiver on them. But the thing is, UDP is correlated. That's the part that we didn't understand. So we have a few hypotheses. A few of them has obvious flaws in it, like if TCP is not related, why is UDP related? Because after all, you're just sending packets through, right? It seems like there's something else about interaction of how TCP behaves. If not, the UDP is having very good correlation, 0.7, 0.8 correlation coefficient with RSSI and CINR.
What do you correlate with UDP? Throughput?
Throughput. This is good put. This is exactly good put. So what I plot is actually good put in megabits per second. So it picks off at 10 megabits per second because UDP IPERF sends at 10 megabits per second. We send it at 10 megabits, so that's the maximum we can go. That's all. So if you actually shift the line down and only take CINR that is below 25, it's even better.
Is there a way you can figure out how many retransmissions you're doing on the TCPN?
No. Or TCPN, yes.
Because it looks like, I mean, if you're dropping that many packets, you gotta be retransmitting like crazy.
Yes and no, because TCP was shorter. UDP is easier to look at how many packets you have to drop. TCP is really hard. TCP is really hard because your window size will cut, and that itself is going to affect how much you transmit. And this is 10 seconds IPERF, so this is actually not representative of a long-lived fruit. That's the problem with the large RTT in the mobile networks that is very much underemphasized. So one thing, if you look at the latency, we are talking about 90 millisecond RTT across the network in the mobile networks, right? This is very, very large compared to Wi-Fi, so they don't really provide you low latency. But why do they claim that? The only reason is because 3G is giving about 150 milliseconds, and 2G GPRS is giving you over 200 milliseconds of RTT. They are better. That is what you can be for sure. They are definitely improving in throughput, latency, and most of this stuff. But compared to what academians are used to in terms of Wi-Fi, no, they are definitely very far off. So okay, we took the same look at delay metrics, so latency and jitter. We take a look at RTT. RTT actually stabilizes to be about 80 millisecond or 90 millisecond when the signal strength is large. So if you're below 20 dB, like exactly what you say, there's retransmission, signal strength, and then it starts to be correlated, right? Before that, the correlation is 0.4, 0.3, but once you take anything that's below 20 dB, you get actually much better correlation that is up. by about 0.2 or 3 on average. So there is definitely some effects of retransmission on the wireless as long as your signal strength is slightly below, like just below 20 dB, or RSSI is approximately about 70 over dBm. You definitely get effects of wireless coming in. And note, this is not due to the backbone network because that backbone is completely not utilized at all. They have a backbone that is able to carry gigabits of data. I can't give you the exact number, so we know about it. They can have a microwave backhaul that is a ring architecture that can carry gigabits of data. Whatever we are trying to put through there is nothing. So this has no constraint on the backhaul. We are not sure if the architecture's backhaul will survive real use though.
What is your benefit?
Pardon?
Do you know the benefits?
Back-
Benefits. Signal benefits.
10 megahertz. 10 megahertz WiMAX. 3 sector, 10 megahertz each. Each base station uses 30 megahertz of bandwidth. Clearwire on average owns about 120 megahertz across the markets they are in. They are probably the largest spectrum owner in the entire states today because they have Comcast, Sprint, Time Warner behind them, so they have a lot of money to buy spectrum. And you'll be surprised who they buy spectrum for. That's a topic for after the talk. So what we see is that the performance of a network can actually be very much predicted by the signal strength you observe. This is good news for application programmers, right? Like I'm an application, I take a look at the signal strength that the device driver is giving me, I actually know how well I'm going to perform. For example, Shrita's idea of cache and forward, if you use it on a mobile network, you can actually just look at this and go, yeah, I'm going to have a difficult time, I'm going to just wait. Yeah. So this actually is a way, it's actually a quantification of that fact, right? It's a quantification that mobile networks actually does behave that way. So if you're below 0 dB, forget about it. Your noise is stronger than your signal. We all know theoretically you're done. You're done for. So anything from 0 to 10 dB is actually difficult. You get signal, you get no signal just because of the fluctuation and so on. And 10 to 20 dB is very restrictive web serving. Don't expect to do any big video transmission, watch Hulu or whatever. No, it's not going to work. 20 to 30 dB, you are getting very, very good signal already. For all good purposes, this is your DSL line and so on and so forth on the move while driving. Yeah, anything that is above 30 dB, you're no longer limited by the wireless. It's really just how much you're paying for, you get everything you pay for.
So excuse me, is that you look at CSLR over time interval and take the mean value here?
Pardon?
So is that true that you measure the CINR over a fixed time interval and calculate the mean value and project it?
No, it's based on the measurements, right? So we take a CINR, then we take measurements for over the next minute, and then we take and then we correlate this value with the CINR.
Yeah, so this is essentially a sample mean.
Yes, it's a sample mean.
Okay,
No, definitely it's a sample mean because note that it's actually the fact that it's well correlated also means that the signal actually stays in fact, that's the next slide. Perfect.
So if the sample mean, but you didn't look at the variance.
We have numbers for the variance in the paper.
Which paper?
I will put up a technical report on my website. So that, because this is a paper under submission, so we are happy to put up the thing. We don't care.
Okay, so you think the sample mean matters, but the variance doesn't that much.
Variance, this is the next slide. So we take a look at the variance. So clearly, yeah, mean is misleading, right? Anybody who studies statistics knows about the book that statistics lies, right? And we take a look at the temporal variance, right? So how much does the signal really change temporally? On a signal where we get about 20 dB on average, we have a standard deviation of less than 0.6 dB. So it's actually very good. The signal actually stays fairly constant as long as you are not moving. Okay? So even that is like 0.18 dB per second on average. So the variance on a single location is not significant. It's not much. Note, this is Mountain View terrain. This is not center of New York City. The middle of New York City at Central Park will have very, very, very different experience. And someone else has to measure that like we have. Spatial. Spatial variation is about the same number per meter with standard deviation of 0.42 dB per meter. So you do expect changes in your signal strength over seconds or minutes depending on how fast you're driving. Right? WiMAX in theory is supposed to be able to take you to 70 miles per hour. We have not tested that because we do not have enough base station across the freeway for us to test that. And I'm not about to drive illegally at that speed along the road. So the other thing that we actually took a look at is footprint of a base station. So you were saying, is it correlated with distance? We'll see. The thing about distance is we calculate a path loss. If you can calculate a path loss, means it's very correlated with the distance. You can actually just use the distance and predict what is going to be there. So the standard equation is the one on the top, and there will be people who tell me that there's more complicated equations to describe this. They're all based on this. If you reduce the Stanford intermittent model or even the Hatta's model, they all reduce to this. So you don't gain anything by using a more complicated model. We take a look at the plot. So what you see on the blue line is actually the loss exponent calculated based on the sample size up to the log of a certain distance. So the problem here about calculating path loss in this sense is because the way roads are built, they're not evenly distributed on the ground. Right? There's a lot of experiment that goes to some desert, put the antenna up there and they start to walk a linear line out. Yes, they get uniform sampling across ground. In a real network, you don't get that benefit. So what happens is that you have sampling bias in this. So we try to find the one that is best correlated with the equation, right? So you are going to have a lot less data out of the cell at the further distance and very, very near to the base station and a lot in between. That's just because that's how networks are deployed, right? You put it on the top of the building, I can get closer to the building than the nearest road itself. So the red line is actually the correlation coefficient of the data up to here based on the equation over there. So if you take a log, so it is just linear because this is log 10 of the distance. So you can actually calculate the correlation coefficient to see how linear the thing is and what is the variance.
What is the correlation coefficient here? Not to correlate.
We will correlate the log 10, the log of the distance with the RSSI or CI now.
I think here, if you look to your chart, it's just your data is like slope is kind of linear. If you just take the just the least square fitting to the RSSI values, you
So,
might get the path loss value like I think.
Correct. No, that's exactly what we did. So if you take that, you take the log of the distance, and you do mean square fitting, it's exactly the equation you use to calculate correlation coefficient. That is minimizing the mean square error. Minimum mean square error is exactly what correlation coefficients are designed to do. So correlation coefficient actually divides out the standard deviation so that you get a value between -1 and 1. So are you negatively correlated or positively correlated? That's exactly what this does. So we're trying to minimize this metric, right? That's the best fit, right? So when this point is the lowest, this is the value that is closest to the fit. This is where the data is closest. But even that, you still see significant variation, right? There are nice things like Mountain View, they give you fairly nice because they're just flat. Stanford actually is a bit nasty because we have taller buildings because of Stanford Hospital and so on. And we have more trees. So it actually gives you variation. So it's actually not easy to calculate a path loss number for urban or, this is not even urban, a suburban area. Yeah. So that is what we observe. It's like, yeah, can we correlate with the distance? Maybe, but the problem is we can't get the number for the correlation. So in theory you could, but in practice you don't know the number.
But you can always get the upper bound, like this.
Yes.
Say it's at least 6 times.
Correct. You can always try to bound the data and define how much you're willing to tolerate in terms of outage. Then it will really define on what you are happy to take as outage. Will you take this patch here as outage or will you not? So it becomes fairly arbitrary, it becomes slightly less scientific, which will eat some people, might not eat the operational guys. They're clearly not very concerned, if you ask me. So okay, taking a look at the footnote of footprint of a base station, right? I know you guys are deploying WiMAX base station, and you guys are probably more interested in this than other people. Each color on the picture is actually represents signal from a base station. So if you see a circle with two colors on it, means that spot itself, we see more than one base station. We see actually two signals. So if you take a look at that, is actually what you see in Stanford itself. There's this big red spot down at the below. Wait, but that actually does not that far away from a base station. It is completely no signal there because there is a canopy of trees covering it and there's undulating hill. It's very, very dependent on the terrain itself. So when mobile network folks goes around saying that we deploy a network and we're going to do surveying, there's a good reason for it because a lot of times it boils down to the experience of the surveyor going to the actual ground and going, oh my, this is not going to work. There's no way you can plan this in advance because these folks there, by the way, Stanford professors, that's where the housing is, decided to grow a lot of trees on their house. They're all covered. By the way, they're complaining about their internet sucks too, so I don't know why. The other thing that we look at, we have two sites on Stanford University. If you take a look at the right side, this is where the Mayer Library is. You see this very nice separation of the sectors. So these are 120-degree sector antennas with 10 megahertz on each sector. So that's how they do the cell planning. You see this very nice property sometimes. And then you get this very nasty mix-up property near the Beckman Hospital building. So it's really so dependent on terrain and reflection and other stuff that it's very, very hard to predict. What mobile folks does is they buy very, very detailed maps on alleviation of the plane, clutter, and so on. But what they can't predict is that we have a building right here that is glass and reflective glass. So it reflects everything. So that is the building where we know that if you put an AP on one side, you can't even get anything from the other side, right? And we are looking at 2.6 gig here. That is the approximate bandwidth. 2.5 to 2.6 is where Clearwire usually operates. Okay, so you can't really predict too much because you might plan all you want. Tomorrow somebody put up a building like that. You have no say on it at all. Absolutely, the city council, the town council might. You don't. So it seems like planning a cell is actually a very, very complicated affair. So what we concluded was this 4G network gives you really good bandwidth compared to what you have from 3G. Fantastic. You're getting DSL quality on the move while driving. This is great. And it's giving you a very, very wide area coverage, right? How many Wi-Fi AP do you need to cover the entire place? A lot. Stanford has a lot of Wi-Fi APs. Not even this coverage can be achieved, right? But this is like 2 base stations with 3 cell sectors. That's all it took to cover that big a distance in the area. The not so good problem is these spots and variation will always exist. It's just not viable for a company to try to cover everything. They're not going to do it. It's crazy because they are a for-profit company. They're going to go under if they start doing charity work like that. And it's really very high latency as compared to things like Wi-Fi. We are talking about 2 or 3 times more. So what does this really mean to interactive application? What does this really mean to people that's trying to game over the mobile network while your friend is on Wi-Fi? Not very advisable if you ask.
Why is the latency higher?
Is the way mobile networks are designed. So even on the first hop link, the official number that they're willing to commit is that RTT will be below 20 milliseconds. Wait, that's bigger than Wi-Fi already, just on the wireless link. We're not calculating the microwave backhaul and everything. The other thing is, at the back of their network, everything pipes to something called ASN gateway, which is really like a SGSN or RNC in a 3G sense. Those things, everything goes there and everything goes out. So you could be at California and your packet is coming out to the internet at Seattle. That's normal. Right? So think about how much more distance you're hopping around in the internet just because of that. The number of hops is big. In our data, we actually have trace route data. So it's quite a few hops.
So the first thing you said was the wireless link RTT itself is
Correct. Because of scheduling. Just because the wireless folks decided that we should schedule. You guys are wireless folks. So and they do the scheduling. And that does add up to RTT. So whenever people decide scheduling algorithm, throughput is always the we are looking for throughput. Yeah, we have throughput. Problem, okay. Yeah, not so nice. So the thing that is not clear now is how much can you bring down the latency if you give a priority to a certain class of traffic. And WiMAX standard does have that. It's just not clear how much it will bring down, and they have not configured that to work yet, so there's no way you can know that. I'm not sure if that number will ever be public because there's no way you can control what they configure as that class of traffic. Right? So we'll see. So I'm going to the second part of the talk that's slightly different from the first part. So we are looking at something that is like 4G, the next generation, and we ask ourselves, what should we do then, right? Is this not a perfect network? We want our perfect network. That's what academians are, right? We strive for the perfection. Let's build another wireless network. But we have built quite a few, right? Quite a few today. So the idea that we're trying to promote is very simple. In fact, somewhat naive or obvious, nearly unappreciable in nature. Typically, we see a lot of networks around us today already. Switch on a cell phone, you see AT&T, you see T-Mobile, you see Verizon. Why do we need to build another network? There's no real good justification for that. But all of them are off limits. If I'm stuck on AT&T, I'm stuck on AT&T. Okay, maybe I can roam. Maybe AT&T will allow me to roam on Verizon network. But wait, suddenly I am having better AT&T signal. Can I switch back? No, roaming doesn't allow you to cross the boundary between networks at all. Roaming just allows you to use another guy's network and stick onto his network. So you have to make a choice. It's like choosing your own poison. And also we have a lot of Wi-Fi networks. Wi-Fi networks are all around us, but there's nothing we can do about it. There's no way we can use it, right? So our goal is to just move across this sea of wireless access and get the best signal that we can have, right? It's like, why do we want to build yet another network when there's so many around? So the problem is clearly, even if you build another network, wireless network, professionally dump a lot of money, a company still have to survive. They will never cover everything. So our first step is really just to become radio agnostic, because radio come and go, technology change. Even as 802.16e is being deployed, 802.16m is being defined. You can't be radio specific. The minute you're radio specific, you will always meet with problems in another 2 years, 3 years, depending on where you are. Maybe in US it will be slightly longer, 10 years, because you guys don't change mobile networks very often. So we'll see. So to allow future networks and future technology to be incorporated easily, we really want to move along and be radio agnostic. We don't really care about the radios we are doing. This is a very simple idea. To the mobile networks guys, we are actually preaching to the choir in a sense that we just want to use flows. This is exactly how WiMAX, LTE, 3G are being defined. We use flows. There's an idea of a flow, a sequence of packets that belongs to a flow, and we manage everything as flows. So all that we really need to do, because the cellular network already does this, there's nothing to be done there, we're happy, they're happy, is to bring the concept of flows to Ethernet switches and Wi-Fi, right? And the obvious choice, and also by the attribute of where I come from, we decided to use OpenFlow, but that's just an arbitrary choice. We really just want to be able to manage things as a flow and take something as a flow and give it to another network and say, this is a flow. So to do that, we actually took a bunch of switches, Ethernet switches, wireless AP, WiMAX space station. The WiMAX space station picture is probably more familiar to you guys too. Put OpenFlow on that. So even the WiMAX space station, we have a fairly stripped down WiMAX space station. So we got the NEC guys just like what you guys did, and strip out everything else and then put OpenFlow in it. That's it. That's all we did. We put a virtualization layer there, right? And we started to control this network through software-defined networking, so-called. In the sense that the protocol, everything is not embedded in the network, but really embedded in the controller. By that, it allows us to actually do a few fanciful things, which I'll get into next. We actually did a demonstration of how we can improve video quality. So on the left, if you look close enough, the picture is a bit jittery because we added 3% or 7% loss to the wireless link. So you actually get this jittery picture. What we did was naive, trivial, and somewhat stupid. We took the flow, split it into two, duplicated the stream in the network, and then just send it down to the same client. This is similar to what is defined as macro diversity in WiMAX. So you just happily stream down the stream, and because this is a video codec like H.264, they are happy with duplicate. The video stream repairs itself, and it's just better.
Did you duplicate it or did you
I duplicated. I duplicated. It's not ECMP.
So the total amount of traffic flowing to the mobile device?
2 times minus 7%, because we lost 7% independently of each one.
40%.
No, it's still 7% if you do the aggregate. Right? Details. So one thing we did is these two streams actually came down from different technology. We came down from WiMAX and Wi-Fi. So independently, and note the delay is actually different, right? Independently of that, video codecs are perfectly happy about this. They will stick the stream together. So we can actually show how to handle between WiMAX and Wi-Fi just because we have the idea of a flow. We can take a flow from the Wi-Fi and shove it into the WiMAX network, and the WiMAX network will take on from there. What we really want here, if you realize, is that this will only work for video streams, nothing else. But the way we have put a virtualization layer on it, it allows us to do nothing. And we say that we write this controller purely for video stream. And the virtualization layer will take nothing else but a video stream and give it to that controller. My ARPs, my TCP stream, everything else handled by a different controller that just does one route because TCP hates duplicate. So it allows us to customize for the device, the technology, or even the application, because some device only has one radio. To explore this in a larger scale, we're actually in the school engineering, we have 100 of these Wi-Fi APs. We have 2 WiMAX space stations, 1 borrowed, 5 Ethernet switches, and we're actually using this network to serve our group itself. Our group of over 20 people are actually using this for their daily email and everything. So we actually handle production traffic to know that the controller can actually be written so that you can actually really run a network out of it, not just arbitrary video data and some things. So we like to present this as a platform of research. Reason why we want to do this is because we feel that the scope is too big. There is too many things to be done. There are questions that people want to answer, like how do we use such a network? How do we really want to communicate with such a control data path separation? How do we manage the IP in such a network? A few things that I'm actually looking at now are exactly this, right? Like when you cross network and different IP and multiple interfaces, how do you stitch network together? Linux kernel will scream out loud if you give it an IP that is not on the interface, on that interface, and you will drop the packet. So then how do you do all this? Right? There's a lot of issues involved. It's not something that I think any research group will take on alone. So what we present to people as a platform is just integrated management framework for Ethernet, Wi-Fi, WiMAX in general. We have yet had to got our hands on LTE. Not that anyone has built one yet, probably Ericsson has one in somewhere in Sweden. And we present a simple API for controlling flows. So if you want to see an example, we actually can reroute a flow in 12 lines of C code. And all these are available publicly, both in hardware and software. And just using OpenFlow as a software-defined model. So this is my last slide. So our hopes for tomorrow in proposing this is that today what we have is really people subscribing to infrastructure and network. Take the infrastructure and think of it like AT&T and so on, right? You're tied to AT&T. He owns the network, he runs the network, he does everything for you. You have zero customization of the network, you can't do anything for it. Absolutely nothing. Even the telco themselves feel frustrated, right? Like AT&T would want to do something different for their iPhone users. They can't. The gate is made by Cisco and it's defined by IETF. Too bad. So our hope for tomorrow is to just remove that very restrictive matching. And as all computer science people will know, if it's too restrictive, add a layer of indirection. That's exactly what we did. We put service provider in between infrastructure. And by service provider, it could still be AT&T. It's just that now AT&T can go and talk to T-Mobile and say that, let me use your network, right? I know how to manage the network. I've been doing this for longer than you do.
This is an economics problem. Basically.
This is both an economics problem and technical problem. Problem is that the economics problem is something that people have thought about, but there's no technology to base this on, right? It's empty thought. So what happens if you look at DSL, Comcast, and so on? The US government, and I think Congress actually passed a law 10 years ago to say that, oh, we're going to split you from your operation. Your customer facing side cannot be related to your infrastructure side. That failed, simply because there's no technology to be there. We're trying to address the technological side of this, and there are actually people in Stanford University that is trying to address the economic side of this. So what happens is this happens to fall under umbrella not just on OpenFlow, but also on something what we call Programmable Open Mobile Internet Project. It is NSF expedition. Expedition just means we're given a lot of money to do this, and there's a lot of professors in it. So there's an economic side of the story that is being told, and people are actually looking at what is the implication of this, right? What is the implication of enabling AT&T to go to T-Mobile and say, let me use your network, let me use your hotspot, right? And that definitely will provide you better coverage, because more simply is better, right? Now they have the ability to manage and so on. And I'm hoping this actually enrich the interaction between users, network, and so on, and allow you to like customize the device to the person's need, right? If I'm able to say that this YouTube video that I'm showing now is actually more important because I'm showing it as a demo, then me just watching it at home, that makes a significant difference, right? I'm willing to pay for the demonstration. I'm not willing to pay for watching video. But now today we are charged one thing. It's an economics problem. Economics says that you can sell a product at similar cost, you'll get that much on the market. But you can differentiate it. It's a well-known economics theory that you actually can do better, because there are people that's willing to pay different things for different occasions. Just like people giving job talks, right? They're willing to pay a lot for the connectivity. People watching video at home, no, forget about it. You're not going to reap any money out of these people. So I'm going to end my talk here, take questions, and before that I will actually like to thank folks. We know the Clearwire guys. Jonathan is actually a professional surveyor in Clearwire. You know the guys quite well. And everybody else is like, Alan is the guy that's in charge of the innovation network. Ron is actually the research head, and John Saw, if you Google him, he's actually their CTO. And of course, my professors who actually paid for everything, minus my gasoline tank when I drove around. And of course, OpenFlow Wireless is not built by me, but a whole bunch of guys. It's a fairly big project at a certain point. So you can find everything else on my website. I'm going to put up the measurement paper as a technical report up there because it's under submission. But we're fairly happy to put it up for people, and we're going to put out the data. Clearly, that's not everything to the data, but you know how papers are written. We extract what we think is important for our team, and everything else is left there. So I'll put up all the numbers out there because I think that is what is important. Question?